Hi, this is lecture 8, part 1, and we are going to talk about regression trees. Okay? So I'm going to present the concept of regression trees, and I'm going to talk about variable importance in regression trees. I would like to call your attention that the part about variable importance can be also used with other nonlinear models. I'm going to present several techniques that are kind of general and can be used in other contexts as well. Okay? So regression trees, the main reference is our textbook by Hastie, Tibishiran and Friedman, basically chapter 9, and variable importance, the paper by Apley and Zhao, which is also in our Google Drive folder. So let's talk about regression trees. So regression trees are kind of flexible, non-parametric predictive model, and it's based on a recursive partition on the input space. What's this input space X? Is the space defined by the explanatory variables. And I'm going to be very clear about what I mean by this recursive partition. It will be clear in a moment, okay? And it's model that has a hierarchical nature. So we are going to make sequential splits in this input space, and the later splits will depend on the previous ones. Okay? And a single regression tree has this nice advantage of being interpretable. Basically, we can explain a regression tree in plain English. Okay, so we can just talking like we can describe what a regression tree is doing. Okay, so it's very intuitive, very intuitive model. Okay, and it can handle very easily both categorical variables and missing data, which can be treated as a category. Okay. What's the main advantage, as we are going to see? It's highly unstable. Because of the splits are sequential, if we make a bad decision, this bad decision will propagate over the tree. Okay, so but there are easy fixes for that. Basically, because it's very unstable, bagging and boosting will help us a lot, and we are going to see during the second part of this lecture how bagging and boosting can help us. Of course, no free lunch. We can fix the instability of the tree, but we have a price to pay. And what's the price to pay? We are going to lose interpretability of the model. Okay? So let's see how it works. Imagine that we have a two-dimensional space, so we have like two explanatory variables, x1 and x2. Okay, and we are going to decide to split x1 on point C1. So basically, we are going to make this decision: is x1 less or equal C1? If yes, we are going to move to the left. If it's no, we're going to move to the right. Okay. So basically, we are making this region. Okay. And now, first, I'm going to describe how to make the regions, and then after that, I'm going to describe what we are going to do with the regions. Okay. But basically, imagine that we have points spread all over this region, the defined by x1 and x2. We splitting the space in two subspaces. The one where x1 is less or equal to than c1, and another subspace where x1 is greater than c1. Okay? And then we can come and make another decision, and now you see here why I'm saying that it's hierarchical, because I'm going to take the first split and I'm going to look to the cases where x1 is larger than c1, and then I'm going to ask another question. For the points where x1 is less than c1, is x2 for the point that x1 is larger than c1, is x2 less or equal c2? So we are making here a second split. and then we can make a decision, an answer to the question, a yes or no. And can we do another split? And now we are going to take the subspace where x1 is larger than c1, x2 is smaller or equal to c2, and then we ask again if x2 is smaller or equal c3. So we have like another point here, c3. Okay? And then we can try another one. Now look into the case where x1 is in fact smaller or equal c1, and then ask another question. Is x1 smaller or equal c4? And then we have here another division. So in the end we have like one region here, another region here, another one here, another one here, another one here, another one here. So we have like 1, 2, 3, 4, 5, 6 regions. 1, 2, sorry, 1, 2, 3, 4, 5, 6, and we have here like 1, 2, 3, 4, 5. So what do we have here? We have like one region here, a second region here, a third region here, a fourth region here, a fifth region here. So you have 1, 2, 3, 4, 5 different regions. Okay? So what we are going to do with these regions? So as I mentioned, we have like 5 different regions that we are labeling R1, R2, R3, R4, and R5. Okay? So what we are going to do, we are going to estimate a local model. So we are going to have one model concerning the points that we have in this region, another model concerning the points in that region, another one here, another model here, and another model here. Okay? So we're going to have local models. So we split the data, and we are going to construct local models for different subregions. Okay? And how complex is the model? In fact, it's pretty simple. We are basically going to take the values of the dependent variable that lie on each specific region, and we are going to take the average. So for example, the local model for region 1, okay, will be the sum of observations of y which lives in the region where the covariates belong to R1, so this is an indicator function, divided by the number of observations in this region. Okay, so this is the first local model. So the model is pretty simple. So basically imagine that's like a constant by parts model. So within each region we estimate a constant model. Okay, and these partitions are determined sequentially. Okay, and I'm going to give examples about that. So an example, take for instance that the case where we want to predict the log wages of baseball players based on the length of the career in years and the number of hits. Okay? So on the left side you have the tree structure. So basically and on the right side we have the data points. So here we have a scatter plot of hits and years. Okay, and these are the points, and we make like 3 regions. So the first one is that for players with less than 4.5 years playing. So what we are going to take, we are going to come to that region and look at the wages for each one of these players here and take the average. The average, like the log wages are 5.1. Then we are going to do the same thing for R2 and the same thing for R3. Okay? So now let's make a more formal definition of a regression tree. So let's see a more formal definition of the problem. So let's write our vector of explanatory variables as xt. Okay, so we have like p of explanatory variables, and our dependent variable we can write as the condition expectation plus an error term, and this condition expectation we are calling it f. Okay, and it's potentially nonlinear. The regression tree idea is to approximate this function f by basically a piecewise constant function. Okay, so basically it's a sum of a weighted sum of indicator functions, where these indicator functions are basically indicators if the observation of xt belongs to the region k. So it will be 1 if, so ik will be equal to 1 if xt belongs to that specific region and 0 otherwise. So basically that's the model. So it's a piecewise constant model. So it's like a sum of basis functions, but our basis functions are these indicator functions that defines these regions in our input space. Okay, so basically the approximation f is equivalent to a linear regression on k dummy variables. Okay, where these dummy variables are, as I said, indicators of each one of the regions defined by the tree. Okay, and of course this ik function is a product of indicator functions, because the indicator functions that define this sequence of decisions. So we have here one indicator function that if x1 is less or equal x1, and this so that region x5 will be the product of 1 minus this first function here times another function, indicator functions x2 is less than c2. So basically R5 will be defined by 1 minus x1 less or equal c1 times 1 minus x2 less or equal c2. Okay, so this defines the function that the indicator function that defines region R5. Okay, and so to make this notation even more formal, let's assume that we have a number of terminal nodes or leaves of the tree, so the last nodes of the tree, and which define the regions, and we are going to say that we have k of these regions. So capital K is the number of nodes, the number of regions, and n is the number of parent nodes. Okay, so a tree, imagine a tree like that one. We have 1, 2, 3, 4, 5 terminal nodes. So k equals to 5, and we have 1, 2, 3, 4 parent nodes. So n equals to 4. Okay? And different regions will be denoted by R1 up to R capital K. The root node will be at position 0, and a parent node at position J has two split nodes at positions 2J plus 1 and 2J plus 2. With this numbering, we can identify exactly the structure of the tree. Okay, so each parent node has a threshold, a split variable associated with it that we are going to call x of sjt, and sj belongs to the set S that's 1 up to P. Okay? So basically, we have here the root node at position 0, and then we have like two nodes. Okay? This node will be at position 1, and this one at position 2. Okay? Let's take the position 2. We are going to divide it again. So this will be like 1. This will be 2 times 2, 4, plus 1, 5, and this will be 6. Okay? Because here, if we split this node here, we are going to have like 3 and 4. Okay? But each decision, we have a variable associated. Because at root 0, at node 0, we have x s0t less or equal some threshold c naught. That's the decision rule involved in this node here. At node 1, at parent node 1, we can have another variable where you're going to ask if it's less or equal a certain threshold, and so on and so forth. Okay? So at each node, we have an index of which variable we are using to create the rule, okay, to decide to which side of the tree we are going. And let's call this J and T the sets of the parent and the terminal nodes. Okay? So the number, the indexes that represents parent and terminal nodes. So here, another example. So we have a tree with 4 different regions. So we have region 1 here, region 2, region 3, region 4. And this parent node 0 that gives terminal node 1 and parent node 2. Parent node 2 gives parent node 5 and parent node 6. And then I'm splitting parent node 5. That will give me terminal node 11 and terminal node 12. So which are the sets of parent nodes? 0 to 5, and the terminal nodes 1, 6, 11, and 12. So this is great because if I give you J and T, you can draw the tree. You draw the structure of the tree. Then if I complement with the SJs and the thresholds, CJs, then you have the full structure of the tree, including all the parameters, right? So it's very easy way to describe a regression tree. If we want a more complicated stuff, but to write everything in a single formula, we have a mathematical representation here. Don't really bother too much about it, but what just is important is to see that a regression tree will be a weighted sum of these functions B, and these functions B are basically a product of indicator functions as described here. So with these functions basically can mathematically describe any regression tree, okay? In practice we are not going to use it, this notation here, this expression, but it's just for you to see that there is a very clear mathematical model behind the tree. Okay? So, what's the idea? We choose a split variable xj and a threshold c, and we want this threshold to decrease the sum of squared error. Okay? So we have a data. Imagine that we have data, y's and x's. Okay? T equal to 1 to capital T. So this is our data. And we write a model like this. And we want to construct a model that has the smallest error possible. So what we are going to do is a very simple approximation. So what we do? Okay, so imagine that xt belongs to R2. So imagine that we have here x1 and x2. So what do we want to do? We want to find the split either in x1 or x2 that decrease the sum of squared errors. So basically what we start with no split, we have just a constant model here. So we are basically saying that no split, the model is yt equals to beta plus ut. So the estimator will be just 1 over t, sum t equals to 1, t yt. So it's just sample average. Okay? So now, can we improve on the sample average? So let's look for the best split variable, either x1 or x2, and the best threshold. So assume that we are going to do a greedy search, like testing all possible thresholds over x2, all possible thresholds over x1. So we try, I say, putting a threshold here, putting a threshold here, putting a threshold here, or a threshold here, or a threshold there. But in the end, we find that this threshold is the best one. So we make that split. So we are going to take the data in this region, take the average, and take the data in that region, take the average. So with one split, we basically say that yt will be beta 1 if, in our case, x2 is less or equal C2 plus beta 2 if x2 larger than C2 plus the error. So how we estimate beta 1? Or beta 1 is just the sample average number of y's in region 1. We are going to take yt times x2t less than C2. Takes the sample average here, beta 2 in the same way. So we compute local averages. So this with 2 splits. So we continue like that with 3 splits, 4 splits, 5 splits. Okay? And we are going to do that until get a fully grown tree. And the good thing is that when you start like 1 split, you can always exhaust the splits on one side. So for instance, you make this split, you can continue like this way, until you get to an end where the number of observations in each region here are too small. Like this is a kind of a definition that we make, that's a hyperparameter. So let's say if we have less than 5 observations in each region, we stop the procedure. So after we finish here, we continue growing like here, and then here, and then here, and then there. And we can like have a fully grown tree. This is the fully grown tree. After you have the fully grown tree, what we are going to do is start pruning, because the fully grown tree will overfit. So after we grow the tree, we are going to remove redundant splits. So that's basically what I'm going to explain in the next few slides. Okay? Hope it's clear. So as I said, for each split we have 2 new regions, and we are going to make these splits in a sequential way. Okay? So this is an example of a region induced by a regression tree. That's the tree that we have here, and that's like in 3 dimensions. Okay? Why we have this plot here on the left? Because these kind of splits are not allowed. They are not allowed in trees, but these are not like recursive. So one region is not nested into the other. Okay? So these kind of regions are not allowed. Okay? So as I said, imagine that we have grown a very large tree that we are going to call this calligraphic T-naught. Okay? So we stop growing the tree when the number of observations within each region reached the kind of lower bound. Okay? So This is a very complex tree, as I mentioned, overfitting a lot. So what I'm going to do, remove irrelevant splits. And we are going to have a parameter alpha that will kind of regulate, put discipline on how we prune. We don't want to prune too much, okay? So basically what we want, we define a tree that is nested into the T naught, okay? And we define a loss function that is the sum of square errors, okay, plus a penalty term, where the penalty term here, what's that? That's the number of regions, okay? And this is a kind of user-defined. Alpha is user-defined, okay? And basically what we want to find the best optimal tree which minimizes this cost function. And of course, how we select alpha, it's usually conducted by cross-validation. Okay, so we select like the regularization term by cross-validation, and we find the best tree that's nested in the fully grown, very large tree that minimizes the cost function C alpha T. Okay? So, as I mentioned, the tuning parameter governs the trade-off between tree size and goodness of fit. Large values of alpha results in smaller trees, and conversely, for smallest values of alpha, we have a large tree. Okay? And so for a given alpha, it's possible to show that there is a unique smallest subtree alpha that will minimize our criterion. Okay? And we call the weakest link pruning that we are going to collapse the internal node that produces the smallest per node increase in the cost function. And we continue like that until we kind of reach the root node tree. Okay? And basically we show that if we do this sequence by the weakest link pruning, we can find the optimal subtree. Okay? So that's an example of a regression tree for the baseball, the log wages of the baseball players, right? So you see that you have many other variables, not only years and hits, but you have like putouts, walks, runs, RBIs, and so many variables that define the tree. So that's the trees that like to predict log wages of baseball players. Okay? And we can look for this example how the mean squared error that we have here, okay, on the y-axis varies with the tree size on the x-axis. So we have here the black lines are the training set, the brown line is for the test set, and the green line is for the cross-validation. And we have these bounds here because the authors show, this is an example in the book. Basically you can try different values of training, cross-validation, and test, and this is kind of the dots are kind of the average value along all the possible choices of training sets, for instance, and the bars indicates like the maximum and minimum values. Okay? All right, so we know how to grow a tree, But how can we measure the relative importance of a variable in a tree? Okay, so a very simple way to measure that is to use the measure of relative importance. Okay, so we can the relative importance for the I of covariate in a tree T will be the sum over the parent nodes, because remember, a covariate enters the tree by defining the split in a parent node. Okay, so we want to measure, okay, the decrease, okay, in terms of RMSEs that variable induces by a split. Okay, so this delta is the improvement in squared error risk over no split. So as I said, if you have no split at all, you have the average. Then you're going to select a split that improves on the simple average by computing two local averages. Okay, if the tree is a tree with just one split, okay, so we have here the variable x0 that defines the first split. So the relative, so you have just one variable, the relative performance is just, the relative importance is how much this split here reduces the MSE of no splits. Okay? So imagine now that we have like a tree like that. So the second one is still x0 and the first one is x1. So the relative importance of x0 will be the decrease in MSE of the first split and plus the decrease in MSEs of the second split. And the relative importance for the x1 will be the decrease in MSE of the third split, and so on and so forth. So we can compute the relative importance of each variable, okay? I hope it's clear. Okay, but then you can say, all right, this gives us like a measure of importance, but can we tell something about how nonlinear is our function f? Remember, we are trying to approximate this function, okay? So this function f is equivalent to as a function of x1t, x2t, xpt. And let's say that we want to know how this function, how nonlinear is this function, what's the shape of this function. And of course, it's sometimes very difficult to show that because we are usually in high dimensions. So there are some sort of ways to overcome that and to give a kind of an idea about the shape of the function. Okay? So one thing is called the partial dependence plot. Okay? So it basically shows the marginal effect of one or two features have on the predicted outcome conditional on the others being fixed. So we fix some of the variables and we show how the predictions change if we change one or two variables. Okay? Yeah. So we can use that to show if that conditional on the others being fixed, if the relation between the output and one or two input variables is linear, monotonic, or more complex. Okay? And for instance, if the model is linear, the PDP will be always linear. Okay? We define the partial dependence function, okay, that we set, for instance, x1 and x2, and imagine that we want the effects of x1, okay? And we want to know, we define the function f1 of x1 is the expected value taken over the distribution of x2 of the function f(x1) and x2. So we are averaging over the distribution of x2. Okay? And the partial dependence will work by marginalizing the model output over the distribution of x2. Okay? So basically, the partial dependence plot is a plot of the partial dependence function f, which is estimated as the weighted average of the function, the estimated function, the tree function of x1 and x2, but taking the average over the x2, the variables that we are conditioning on or marginalizing. Okay? What are the advantages? It's very intuitive and easy to implement. Disadvantages: it's only viable with two variables, because otherwise you cannot plot more than two variables. Okay, and it's basically to make sense if we assume that the variables for which the partial dependence is computed are not correlated with the other variables. Okay, so how we overcome this drawback? We can use two alternatives. One is the accumulated local effect plots, okay, or look at individual condition expectation curves. Basically, we plot the partial dependence function against x1 by holding x2 tau fixed for every value of tau. Okay, so we make lots of plots. Instead of marginalizing, we are basically holding one of these variables, the control variables, fixed. So let me show you an example. This is a GDP of 200 observations where x1 is a uniform plus a normal, so it's kind of weird random variable, and x2 is x1 plus a normal random variable. Okay. Suppose there are no dependent variable. So plot A is a PDP plot. Okay? So basically what we are looking, we have here, so we are looking at this, we have the x1, the scatter plot of x2 and x1, okay? And here what we are looking, that's curve here is the marginal distribution of x2. Okay? The partial dependence plot at the point x1, okay, averages fx1, x2 over the marginal distribution of x2. So you see that's taking the average over all this distribution here. Because x2 is distributed, that's the range of x2. It goes from here to very small values to very large values. See, here and there. So you are averaging for in regions where there is no value of x1, and so it's kind of weird, right? So there's a kind of conditional distribution plot, the M plot, that's using the conditional distribution instead of the marginal distribution. So we are going to average over the conditional distribution of x2 given x1 is equal to lowercase x. So instead of averaging over this full distribution here, the conditional distribution is much narrower. So it makes a lot of more sense to average over the conditional distribution. Okay, so this is the M plot. So it's a much nicer way to see how this, what's the shape of this estimated nonlinear function. Okay. The accumulated local effects, okay, is a bit more intricate, okay, where basically what we are going to plot, we are going to take the condition expectation okay, of the derivative of the estimated function. Okay, this is given by our regression tree. We're going to take the derivative with respect to x1, conditional on x1 equals to some z. Okay, and we are going to take the expectation of this term with respect to the condition distribution of x1 given xt. And then we are going to integrate in a neighborhood from z naught up to x1. So this is equivalent of this expression here. Okay? And this plot, we are going to look not at the, we are going, instead of averaging with the condition distribution, the function itself, we are going to look at local averages of the local effect itself. Okay? So we are looking directly into the local effects. Okay? So it's a much nicer way to try to uncover the real relationship between these variables. Okay? So, of course, in terms of variable importance, is something tuned to regression trees, but PDPs and accumulated local effects or M plots like here, you can use these tools to any nonlinear machine learning model. So you can use that for neural networks, for deep neural networks, and so on and so forth. Okay, so that's for our block 1. I'll see you on block